Now let's talk about this problem. And this problem requires us to find the total impedance of the given circuit. The circuit consists of a source voltage with an amplitude of 5 volts and a frequency of 12 kilohertz, and a resistor, an inductor, and a capacitor which are arranged in parallel. The value of the resistor is 100 ohms, the value of the inductor is 15 millihenry, and the value of the capacitance is 0.022 microfarad. So there seems to be some sort of error in the typing, so that's supposed to be microfarad. Okay, now even though it requires us to solve for the total impedance only, as an exercise, we'll extend our solution to solving not just the impedance, but as well as the phase angle, the amplitudes of the current, and we're also going to plot the waveforms for the current and the phasor diagram for the current. Why are we plotting the current instead of the voltage? Well, first of all, the voltage across each of these circuit elements are the same, so it does not provide as useful information if we plot the current instead, because with the currents we also get the magnitude, but if we just plot the voltage, then all magnitudes are the same and we just get the relationship of the phase angles relative to each other. So it's better in parallel circuits such as these, it's better to plot the phase, the currents for the circuit. Okay, let's begin. So we have the given values, as we mentioned before. We can easily solve for the other given quantities as the following. Omega is equal to 2 pi f, which is equal to 24,000 pi hertz. Okay, I didn't bother to write down the actual number because I'm going to put this in MATLAB anyway to make the calculations faster and easier. The conductance, which is the reciprocal of the resistance, is equal to 0.010, and the unit for the conductance is Siemens, or sometimes we write it as just S. So just for comparison, I'm going to write this as millisiemens. For the inductive susceptance, which is the reciprocal of the inductive reactance, which is equal to 1 over omega L, we solve it as 8.84 times 10 to the minus 4 Siemens, or 0.88 millisiemens. And for the capacitive susceptance, which is equal to omega times C, this is easily solved as 0.017 Siemens, or 1.7 millisiemens. Okay, now it's probably clearer now why I wrote this in millisiemens, because it's easier to compare between the susceptance and the conductance. We see the conductance has the largest value, while the susceptance has about 1.7 and 0.88 for the capacitive and the inductive susceptances. And since these two susceptances are 180 degrees out of phase, these values will cancel each other out. We see that the capacitive susceptance is greater than the inductive susceptance, which means that this parallel circuit is more capacitive than inductive. We also expect that the phase angle will be at the first quadrant. Okay, let's take a look if that's correct. So the admittance we can easily solve by simply taking the root of the square root of g squared plus b sub l minus bc squared. Okay, plugging in the values we get approximately 10 millisiemens. Okay, this is understandable because these two values here is just about less than or approximately 10% of the conductance. Okay, and if you, of course, if you take the difference between them, that's even smaller than 10%, which means that the conductance has the greatest contribution among the three. And solving for the phase angle, we get negative BL minus BC over G, and the value in degrees is 4.43 degrees. Okay, again, we expect this to be small because the difference between these two is much smaller compared to the value of the conductance. Okay, let's solve for the amplitudes of the current. Let's solve for the amplitude of the current source first. So this will be V times Y. Okay, now why is this like this? Okay, remember that if you recall, V is equal to IR, but since we're using conductance here, or the reciprocal of the resistance, then this will become I is equal to V times G. So it's the same also for the admittance and also for the susceptance. This will be then equal to 5 volts times 10 millisiemens, which is approximately 0.0501 amperes. For the resistance, this is equal to V times G, 5 volts times 10 millisiemens, which is approximately again 0.0500 amperes. So it's just a very small difference. Then if we continue on to the current across the inductor, we have V times B sub L, 5 volts, 0.88 millisiemens. That's about 0.044 amperes. And then I C naught is equal to V times BC is equal to 5 volts times 1.7 millisiemens, which is about 0.0083 amperes. Okay, so we can make a plot of the source current to be equal to to this expression, which includes the phase angle, the plot for the resistor current, which is equal to this expression. We assume that the phase angle is relative to the resistance. IL is equal to IL naught sine omega t plus 90 degrees, and then IC is equal to IC naught sine omega t minus 90 degrees. Okay, one last thing. We're asked for the total impedance, and the total impedance is just the reciprocal of the admittance. And if we solve for that, this is about 99.7 ohms. Okay. The next step is to graph these values. So here we have in the right image, we have the phase diagram for the currents, and in the left image, we have the phase diagram for the sinusoidal waveforms. We see that the contribution from the inductor and the capacitor is much smaller compared to the contribution from the resistor. So most of the source current comes from the resistor, and that is why the angle between the source current and the resistor is it's small, but it's not very small. We can also see that in the sinusoidal waveform, there's a small shift, which again corresponds to about 43 degrees, which is the phase angle. the shift between the resistor and the source current. And we can see here that the shift between the inductor and the capacitor is 180 degrees, and the shift between the inductor between the resistor is 90, with the inductor leading, and the shift between the capacitor and the resistor is 90 with the resistor leading.